Right, so I'll talk about subsampling, and I actually wanted to start with my motivation for actually trying to look at this problem, which is slightly different from the computational aspect that people have usually thought about different sampling approaches. So the reason I got into it was sort of this problem of large data but small labels. So a lot of the people I work with have very large data sets, right? So there are civil engineers, who have access to profiles of thousands and thousands of buildings from different cities. But really, they don't have as much label data to go with. So they want to do some kind of energy prediction or energy planning for the city, but they have very little data on energy usage for these buildings. So very few of the buildings come with this associated label of what their energy consumption is. Similarly, healthcare records, there are lots of them, but there are very few customer satisfaction ratings that people or healthcare companies have access to. There are natural images that neuroscientists deal with. Right? So they want to understand the response of the brain to natural images, and there are clearly lots and lots of images, a big image pool, right? Billions of images that they can potentially show to a person, but the way the label, or in this case, the response of the brain is collected is by putting a person in a brain scanner. And it's limited in how many images you can show to a person when they are in an fMRI scanner. Anybody who's been in a scanner probably knows that. It's not a very nice experience, right? So you can again think of this as a label constraint scenario where you have a big pool to choose from, but you can only show a small number of images to the subjects to collect their brain response. And the last one I like to mention, and I'll mention a few more, I guess when I show some experimental results later on. So this is a more recent collaboration with some material scientists who are interested in looking at they have a few parameters and they have lots of experimental settings, temperature, pressure, humidity, lots of things that they can, what substrates they use, what concentration they mix different reagents in, that they can change. So lots of settings of these parameters. And of course, they are limited in their resources and how many experiments they can actually do. So they can't synthesize materials under all those different experimental settings, and they are interested in figuring out what is the small subset of experiments I should try out to learn the best about the problem, right? To be able to predict these material properties well. So the question that brought me to subsampling was, given a large pool of data with a label budget, how do we select points for subsampling? Okay? So we'll try to address this question in the context of linear regression, which is probably the simplest setting. I'll actually take a statistical approach to this problem. So we'll assume a statistical model. And to statisticians, this is nothing new. To people who come from our CS theory, who are used to worst case analysis, this is like a model we are assuming, right? So an average, a simple version of an average case, if you want to think of it that way. So we are assuming that our labels y, so there are potentially a lot of them, n of them, come from this linear model where x contains my n data points described by, so every row is a data point, and it's represented by some p features describing every data point. Right? And beta is my set of regression coefficients. Epsilon is some additive Gaussian noise. So in this case, we assume that epsilon are all IID samples from a white Gaussian noise with standard mean 0 and I guess some covariance sigma square I. X for now we'll assume is a fixed data matrix with full column rank. Okay? And so we are in this large sample setting, which means that we have n much larger than p. So n is the number of data points we can potentially collect the labels for. And p is the number of features, and we are thinking of this x as a tall matrix, essentially. So lots of data points and few features for now. Okay? So is the setup clear? So this is a simple stochastic model we'll look at. And we'll address two questions. One is estimation, which is how do we estimate this true regression coefficient vector beta, right? Given a label budget on how many of these y's I can collect. And the second is prediction. I would like to be able to predict the label of some, so z beta would be the label, of some new data point or set of data points. I'll assume there are m data points we want to do a prediction for, which is captured by this matrix z. Now z may be the same as x, but it does not have to be. Okay? So if it's the same as x, you are just filling in the missing labels, whereas if it's z, it's a new set of data that you want to train on some data set and be able to predict on another one. So if people are familiar with the transfer learning setting, then you can also try to think of this as there's some relation between training on one part, trying to predict on something that may be related in some way, but not exactly coming from the same distribution or something like that. So we'll address these two problems of estimation and prediction, and under the following setting, that what if I have a budget on how many of the y's out of the n I can collect. So I'm given a label budget of k. We can only collect k points. And clearly, k has to be at least p if there are p features, right, without making any further assumptions, right? Those are the degrees of freedom, at least in this model. So for k lying somewhere between p and n, if I give you such a budget constraint, then which are the y's I should measure? So again, in some of the applications I mentioned, x would be like profiles of buildings. These are which energy profiles you collect, or different images strung out as vectors in x, or some feature representation, which rain responses to collect, and so on. Okay. All right, so let me first say what is possible with the fully labeled setting. So suppose I did have access to all the n labels, right? Then the standard solution, which is just the least square solution, right? So the beta vector, which minimizes my fit of a linear fit to the y's, is given by the pseudo inverse of x times y, right? So it's the standard OLS solution. And if you look at its estimation error, it looks, so under this linear models, look like this. So sigma square is the noise variance times the trace of x transpose x inverse, where x is my design matrix or set of data points, essentially, right? So the n by p matrix. And the prediction error, so for some z of this solution, the OLS solution, is given as sigma square times trace of z transpose z, z being my test points, and x being my x transpose x inverse, x being my training points, divided by m, where m was the number of data, test data points, z. Okay. So this is all known. It's the standard OLS solution, right? I wanted to point out is that if actually these two problems are slightly different, estimation tends to be harder than prediction, and one way you can see that is if my test points were the same as my training points, then my prediction error here is actually independent of the conditioning of the design matrix or the data points. It only depends on the number of them, right? So if I replace z with x, you just end up with p here. So your solution is, your prediction error is just sigma square p over m, and depending on how many points you subsample, you can essentially just do uniform subsampling. There's nothing more you can learn from knowledge of the data points or design matrix that can help you. Okay? So prediction tends to be easier. You can be off in your beta error or the estimation error, but you can still predict well. So there's a slight discrepancy, and actually that's why for the prediction error, the subsampling is really only interesting to study in the setting where your z might not exactly be the same as x, but it's slightly different, some related but different data set that you might have access to. All right, so moving forward, let me establish, so what our goal is to get to the minimax subsampling, and by that I mean the following, that we look at our expected error, so the error being, for estimation, it will be how far my estimate of beta is from the true beta, and for prediction, it's going to be how far my estimate of the label, right, which is z beta hat, is from z beta, right, and we are interested in what the expected value of the loss function is over worst case over all possible regression coefficients that might occur. And the inf is taken over all algorithms that are allowed to subsample k points. And we'll be referring to a few different sets of algorithms depending on the nature of subsampling you allow. So it could be deterministic sampling, where the algorithm has to just pick k points from the n that are given to you in a deterministic manner. We'll look at random sampling with replacement, where you can sample the same point again and you get sort of fresh noise. So you can go to the field, measure the thing again independently, right, using the same x, but you get a different sampling of noise. Random sampling without replacement, where you're not allowed to sample the same point again. You basically get the same noise level, so it's not useful to collect the same point multiple times. And if I have time, I might mention some brief results on the weighted sampling, which I am not even defining right now. If we can get to it, I'll talk about it later on. Okay. So with this baseline setup, and this being our goal, how does this error depend on k, and what's the best you can make this error using different sampling schemes? Let me mention some prior work in this direction. So probably the most closely related work that comes to mind is from actually classical statistics. So classical statistics calls this problem as the experimental design problem, where there are a bunch of different experimental design criteria people have defined. And in particular, the A optimality and G optimality are the ones that are relevant here for estimation and prediction respectively. Okay, so for estimation, the A optimality is just, it's basically you look at, so this was precisely what the estimation error was for the fully sampled case, right? Without, if S is equal to, is not a subset, it's all endpoints. This was precisely what the objective was. Now we are just saying we are going to pick some excess from that and restrain its cardinality so you can only pick k points, right? This is precisely what the error would be. and just minimize it over all possible choices of k out of the n. Right? And g-optimality is something similar, where we are looking at the prediction error of the OLS for the subsample using a subsample that's denoted by s of cardinality k. And again, from the n, we're looking at all n choose k options and trying to find the one that minimizes this prediction error. Okay? So that's what people have been using classically, and it worked fine when our data sets were small, right? But now n is very large, and we are talking about something like choosing n choose k. So these are now combinatorial solutions, actually, right? Their complexity scales like n to the k. So while classical statistics provides us with these nice solutions, they are just not very scalable. Okay? So we look at how we can come up with computationally efficient algorithms that are still near optimal in terms of their statistical performance. Right? And yeah, let me mention quickly that once you obtain a subset using either of these methods, of course, you can still get the solution, right? Your estimate will just be OLS, right, the standard least squared solution using the subset that you have obtained using either of these optimality criteria. Right? And the way the subsampling helps is it actually helps you improve the conditioning. So you can imagine earlier you had x transpose x inverse. Now everywhere you're replacing it with xs transpose xs inverse. So you can hope to, by intelligent choice of your design points, you can hope to improve the conditioning of your matrix so it has better properties when inverted, essentially. Okay, so this was one work, and let me mention that people have tried to come up with approximation algorithms for these combinatorial solutions. And in particular, there's a bunch of them. I'd like to mention one that's most related and also probably the newest by Avron and Boutistis, which is a polynomial time algorithm. It is a deterministic algorithm. And their goal was not directly linear regression. They were interested in the pseudo-inverse of some matrix X and optimizing its Frobenius norm by picking a subset that best preserves that Frobenius norm. Okay, so they give results of the following form, that they give you a construction for this subset S such that the pseudo-inverse, when I only take the S rows of X, I look at its pseudo-inverse, the Frobenius norm is like essentially, you can think of it as n over k when we are in the large sample regime. We are thinking of n larger than p and k also as potentially, at least scaling like p. Right? So you can think of it as n over k times the Frobenius norm as if you observe the whole matrix. So they were interested in this problem, but it's very easy to realize that these Frobenius norms are nothing but they are related to the objective I just mentioned. In fact, the Frobenius norm of x pseudo inverse squared is precisely the trace of x transpose x inverse. And similarly over here, so you see that you directly get a solution for the linear regression problem. Okay? And yeah, I won't go into the details of their algorithm, but because I'll compare against it in the simulations that I show later on and the real experiments, let me quickly mention what the flavor of the algorithm is. So these are greedy algorithms, and they propose a bunch of them. Here is one of them, where basically they start with all the rows in your matrix, and then they greedily remove one row at a time. So they do this n minus k times. At the end, they are just left with k rows, and that's their subsample. Okay? And the way they remove this is by looking at doing essentially a SVD of the current set of rows that you have, right, starting with the full one, and picking one according to some criteria, which depends on norms and singular values and so on. Okay? And then they keep removing one at a time, do this n minus k times until you're left with k. So I call this a greedy procedure because you're greedily sort of optimizing some criteria and removing rows according to that. Okay. So this result directly translates into a guarantee for the linear regression, and what it looks like is as follows. So it says that using these greedy algorithms, we have a polynomial time algorithm that can output a deterministic set S with size k, where k needs to be, of course, bigger than p. And if you look at this estimation error over all possible betas, it looks like sigma squared trace of sigma inverse over k. Okay, sigma being the x transpose x over n. So that's the sample covariance of my data points. Okay. Now this result is actually not very exciting. And the reason being that if you just did uniform sampling, you would actually get the same result, right? So with full subsamples, you just have your result for the full sample OLS, least square solution, is sigma squared trace sigma inverse over n, and now you just get a k, as if you had uniformly sampled, right? So in fact, uniform sampling, subsampling gives you precisely the same rate. Of course, the k at which that rate might kick in could be different in general. But overall, it's not that exciting of a result from the linear regression perspective. Okay. So yeah, this is one of the algorithms we'll compare against at the end. I also wanted to mention another one, which is actually by Ma, Mahoney, Mike here, Bin Yu, and I guess there was another follow-up paper they had on arXiv, where they were looking at leverage scores and how can leverage scores do when used for the linear regression problem. Okay? And what leverage score is nothing but you look at, it's essentially this quantity. So it's like the projection matrix and you're looking at its diagonals. Right? So the diagonal entries tell you what the importance of each row is in the data matrix, right? And you sample proportional to that leverage score. So you sample a row proportional to its leverage score. And what they had shown was they actually used a slightly different estimator called a weighted OLS. So instead of just having y minus x beta, they were weighting it by this diagonal set of entries correspond with the distribution in there. And what they showed is that leverage score sampling is actually, this is known, is good for approximating the full sample OLS solution, right? And in particular, actually it's known to be good even in the worst case analysis when you don't have the stochastic model with additive noise on top of it. But it is actually even worse than uniform sampling, or can be worse than uniform sampling when you care about estimating the true regression coefficients. So not approximating the full sample solution, but estimating the true regression coefficients according to this model. And they actually showed that you should not actually be doing the weighted OLS, you should be doing the unweighted OLS if you care about getting to the true regression coefficients, but they did not specify what is the optimal sampling distribution which works best for the unweighted OLS. Okay? So, let me quickly mention de-optimality, which is another criteria in classical statistics that people actually use in practice, which maximizes something related but slightly different. It's the determinant of XS transpose XS. So it's like the volume of, so the subset you pick is, it has the maximum volume. Okay? So that's sort of the interpretation here. So we'll also compare against this. So what's our solution? The solution was very straightforward. All we tried was, let's do a convex relaxation of the original objectives. So here are the two objectives. And if my pi, this diagonal thing, was just ones or zeros on the diagonal and 0 everywhere else, so it's a diagonal matrix with 1 and 0, saying which data point we pick, which one we don't pick, and we relax it to, instead of being 0 and 1, to lie between 0 and 1. That's a convex relaxation, right? And we still have the constraint that they all have to be positive and sum to 1. Then this simple convex relaxation followed by a little bit of adjustment. So you have to do this a few times and have a backup procedure, the greedy procedure to fall back on. But these are all details. Essentially, you do this convex relaxation, and we can show some nice properties for it. In particular, what we can show is that you only need, so this, how many times you do it just needs to scale like log n. But if the number of subsamples scales like sigma star inverse, where I'll mention in a minute what sigma star is, times log n over epsilon square, then you can get a relative error approximation. So f-opt and g-opt are the solutions of those optimization problems. And you get a relative error approximation, 1 plus epsilon approximation, to the minimax subsampling objectives using this method. And how large k needs to be, it does depend on the sigma star inverse, but sigma star is actually the covariance matrix of the points that are weighted by the best possible sampling distribution. So it actually tends to be well conditioned. It's not as badly conditioned as the original points. Okay, so you do need a certain number of k to scale like something, which is not too bad, but you get this relative error approximation. And actually, we can show the same kind of results even for, so this is the same method. You add an extra constraint. Instead of allowing it to be from 0 to 1, you force by your solution sampling probabilities to be between 0 and 1 by k. And if you do that, you can actually get a result for sampling without replacement as well. It's basically you're forcing each point not to be sampled too many times. And you get similar results. Everything is the same, except now instead of 1 plus epsilon, we can only show log k. But actually, we have recent results that it might be possible to improve this back to 1 plus epsilon. So yeah, but there are results for both with and without replacement. And so yeah, let me mention a few points about implementation. So as I said, it's a convex relaxation. And in particular, you can write it as a semi-definite program and use any standard STP solver to solve it. But we also give, STP tends to be very slow in practice. So we also look at a projective gradient descent algorithm. So I guess how much time do I have? I can go over the specifics of STP.
About 6 minutes left.
Okay. So I'll just mention the overall main steps quickly, but then go on to showing you some results. So the projective gradient descent is, yeah, you just have your objective function, which could be either of the two optimizations I mentioned for estimation or prediction. a feasible solution set, which is all sampling probabilities, so they have to be positive and sum up to 1, right? And in the case of without sampling replacement, also bounded by 1 by k. And there are some parameters which we can set to some defaults. These are the values we use in our algorithm. And essentially all you do is until your relative accuracy falls below epsilon, you compute the gradient of your objective function. These gradient steps are actually easy to compute, not too hard. You do a backtracking line search to pick the right step size to choose. And you do projective gradient descent. So you do gradient descent and project back onto the feasible set. Okay? So it's a very simple algorithm and it works well in practice. We can show convergence of this algorithm. And also, let me say a little bit more about the computational aspect. So the only one tricky part was that now we are projecting, especially in the case of without replacement, we want to ensure that these probabilities sum to 1 are positive and also bounded in some infinity norm by like 1 by k. Right? So we actually had to project onto the intersection of the L1 and the L infinity balls. And there's a nice trick that I won't go into, but so this thing could be useful in general if you have to take, find the best approximation while your feasible set being the intersection of two convex balls, then you can do it using some intelligent tricks. So what does the computational complexity look like? The gradient computation step is linear. The projection step is also linear. So all individual steps are linear in every iteration. As far as the number of iterations needed, that itself we don't have a good handle on. We can show convergence as 1 by t of the error. But I think in terms of its dependence on n, that can be characterized a bit better. So that's something we are working on. But in practice, it only takes less than 100 iterations for 10,000 data points for very ill-conditioned matrices with exponential spectral gap, and they work pretty well. So let me get to some simulations. So this is, we generated the data first according to some exact linear model. N is 10,000, P is 10, and these are, yeah, you can look up the different parameters. I'll mention a bunch of different results. Uniform sampling, where we are just sampling, right, a k subset at random from the N. Leverage score sampling, which is this, sampling proportional to the leverage scores. Double leverage score sampling, this is something we came up with earlier. It's optimal for another estimator, but not for the Minimax optimal one. But anyways, we were comparing against that. Predictor length sampling, where you just sample proportional to the norm of each row. The convex A and G optimality criteria that I just proposed. And the greedy method of this Ebron and Butius's paper, and de-optimality. Okay? And so here's how the results look like for estimation. So these are for two different spectral decays, exponential and cubic. And we see that the uniform sampling, which is green, and the blue and pink curves or magenta curves being the leverage score samplings, the predictor length sampling being, well, that's the blue one, and the leverage score is red and magenta. They are all much worse. And then the algorithms that do pretty well are the ones that are the convex A optimality, the greedy one, and the D optimality. Okay? And you see this phenomena repeated here as well. So they all do pretty well, whereas all the leverage score based ones are suboptimal. The same result holds true for without replacement also. So this is just the same results without replacement. And these are the results for prediction. So for prediction, you again see that these four are worse. These three do about okay. And then there's the yellow curve, which is the prediction, the convex relaxation for the prediction case, which again does the best. More importantly, so it seems from the simulation results that the D-optimality and greedy ones are competitive, right, to the convex relaxations. But it turns out that in real data sets, that's actually not the case. They appear to be much worse. So here are some results on, this was a CPU benchmarking problem where we had a bunch of, I guess, 209 samples of CPUs with different model parameters, different specifications. And the goal was to predict their performance. And if you look at these curves, then you see that the greedy one actually does fairly worse, which is this kind of purple thing up here. The D-optimality starts out good, but then it's much worse. And the black one, which is supposed to be this convex relaxation, actually does pretty well overall. And notice that this is not even testing when your true model is linear, right? So in real data, you don't know. The true linear model assumption does not hold. But at least leverage scores and things like that, which are going after worst case distributions, tend to work not as well as these things, which are based on off of the linear model. So at least coming to some kind of an average case or stochastic model does give some reasonable results even in practice. And this is comparing the performance of the subsample one to the full OLS solution, right? Because this is prediction. This is just testing for prediction. This is a surrogate for testing for estimation, where we are saying how close you get to the full sample solution. And once again, we see that the results are much better with this convex a optimality kind of criteria that we proposed. And not only for this particular data set, here are a couple more. So this is a data set of wind speed prediction in Minnesota. So you subsample few locations and you have to predict what the wind speed looks like in other locations. This is a subsample of gene expressions. Actually, this was used in the Ma, Mahoney, and Yu paper, where they looked at predicting gene expressions for different subjects using other subjects. And in all of these settings, we again see that these yellow and black curves, which correspond to the convex relaxations, tend to work much better than even d-optimality or the Grady criteria, as well as leverage score and predictor length sampling, and consistently over here as well. Right. So in the interest of time, I'll skip over interpretable sampling, but we also have some results for, because this does not directly tell you, it tells you we are minimax optimal, we are close to it, but what's the improvement over uniform sampling? And we have some results under random designs when we say, what if our design data points were sampled from some distributions? How far are we, when do we exactly gain over uniform, and how much we gain? We have some results for that, but in the interest of time, I think I'll skip over these. But if somebody's interested, you can look at it. So for example, for Gaussian distribution, you can get something like this using this interpretable sampling method, which instead of doing a convex relaxation sample is proportional to the density of the point. And you can show that it's provably better than the uniform subsampling, and you can precisely study when it is. And you can do this for different distributions. Our result is more general. You just have to plug in different distributions to get the corresponding results. So I'll end with some extensions and future directions. So one thing we have looked at is this weighted subsampling, where in some scenarios, you, instead of saying subsample a set of k out of the n, you have a budget that you can allocate to the k points. So for example, when you are doing quantization, you can allocate different number of bits to the points that you, the labels that you do intend to measure. And so we have a result for that. Again, I won't go into the specifics, just wanted to mention that. The high dimensional setting is completely open and would be very nice to solve. What happens when you have many more features than number of samples? How can you do these kind of subsamplings in that setting? And studying the optimality of the number of, what is the minimum number of samples? We know it has to be bigger than p, but do we have the right dependence on other quantities or not? That's also, we are currently studying that. So here are two papers on this topic, and I'd like to thank my student Hyuning, who really did all the work.